Start on time. Now we have the pleasure to have Lavaei here. That's going to talk a bit more about optimization, I guess. Javad is an associate professor in the Department of Industrial Engineering and Operations Research in Berkeley. Before that, he was in Columbia, and then before that, I guess also Stanford, Caltech, Sharif.
Concordia in Canada. So.
Concordia.
A number of places.
Quite a few places. So, yeah, I leave you the floor, Javad, and hopefully we have 15, 20 minutes of discussion.
Okay, thank you. It's my pleasure to be in this wonderful place and talk about the research that my group has been doing in the past 5 years. My presentation is on computational methods for nonlinear optimization problems in power, and I'm going to talk about both formulations like convex formulation and numerical algorithms that we can have to solve the problem. And I'm going to talk about 4 different topics with different level of details. The first one is, how to design computational method that can deal with nonlinearities for just solving optimization problems. The second one is how to do data analytics where we have nonlinearity. And the third one is how to design algorithms. And the last one is mostly initiated by all these activities in the machine learning community, and the question is, how can we just use local search methods, cheap algorithm, and come up with good current cheese? And during the talk, for each topic, I'm going to have demonstrations on real-world, data sets and systems with as high as 13,000 nodes. The first topic is kind of old, like half of you probably have seen it, but I'm going to use it to motivate the rest of the talk. So, a 30-second introduction to power systems. We are dealing with a gigantic physical system with overhead and underground lines, power electronic devices, loads, generators. So it's a very complex system that we use for generating electricity, for transporting that to different cities, and for distributing electricity within each neighborhood. And when it comes to the operation of a power system, the heart of the system is the transmission grid that is in the middle, and at that level there are entities like ISOs, RTOs, and TSOs that deal with serious operational problems. Problems like unit commitment or UC, optimal power flow or OPF, security analysis, and state estimation. So unit commitment usually happens 24 hours or a while before the operation, where we want to decide what subset of resources are good. Like if I have so many generators, what subset should I pick? And that's a discrete optimization problem. The other end of the spectrum is a continuous optimization problem. That's optimal power flow, where we solve every 5 to 15 minutes before operation, and we want to optimize the actual flows over the grid. We should also make sure that we never over-optimize the performance, because with a low probability something could go wrong, and that could lead to a catastrophic failure. So we have to make the system robust and resilient enough. And also, this is a data-driven problem. We go from data to actions, and a part of the data could be wrong. So how can I get useful information from unreliable data? And these problems are complex for different reasons, but there is some common factor, and that's nonlinearity. And due to nonlinearity, there are different types of solutions. For example, if I'm given a surface and I want to find the lowest point possible, I can use off-the-shelf solvers and end up with point A. But in my mind, I want to find the best point possible, and that's point B. But maybe finding point B is too hard, and I need to have a compromise. What if I find a point that is not as bad as A and is not as good as B, and we call it near global? And if we look at the power industry and many other industries, if they can find a global solution, a local solution, they would be thrilled. So first they care about feasibility. Like satisfying laws of physics every 5 minutes is really hard. And if they can satisfy this, they try to optimize it. So even finding a local solution is a challenge. But in the future, if we want to be ambitious, we really want to find a global or a near global solution using effective techniques like local search algorithms or convex optimization, but with guarantees. And guarantees for us are numbers like between 0% and 100%, which tells us how far we are away from the best solution possible. This is like the approximation ratio in computer science. So let's start with convexification techniques. So given an optimization problem, most of the time it's either already a polynomial optimization, or we can approximate it with a polynomial optimization. And by polynomial optimization, I mean I want to minimize the polynomial objective subject to an arbitrary number of polynomial constraints. And it's easy to show that every polynomial optimization has a canonical form that is quadratic. So if you give me a high order optimization, I can always make it quadratic. And that means I want to minimize x transpose mx subject to quadratic constraint. And if we look at the literature of NP-hardness in graph theory and discrete optimization and all those things, they can be traced back to this one. Because all those decision-making problems are hard because of getting quadratic equations as opposed to linear equations. So how can I deal with quadratic equations? I can do linearization. I can write x transpose mx as a trace of mx x transpose and replace vector x with a matrix W in a much higher dimensional space. That's a lifting technique. And to get rid of x, I can impose additional constraint on W. So W should be positive semi-definite and rank 1. If I drop the rank constraint, that's the standard conic relaxation that is called semi-definite programming or SDP. It's a matrix optimization. It's convex. I know how to solve it efficiently in theory. There are practical issues. I'm going to talk about it later on. If there is a rank 1 solution to that problem, I can decompose it as XX transpose. That X is global for the original problem. So that's an instance of a problem that is easy, but this is NP hard. Sometimes we don't get rank 1, and that's where the problem gets interesting. What if SDP fails? Then maybe finding the global solution is hard. And we're going to revise SDP in two ways. We add a penalty to the objective, and we incorporate more inequalities that are called valid inequalities. And we call that problem penalized SDP. If we get a rank 1 solution there, we can decompose it as XX transpose, and that X would be near global. And I'm going to talk about it later on. The geometric interpretation is like this, that if the feasible set is non-convex disconnected, I embed it into a convex set. But if the objective is not right, I'm going to get a point that is useless. By using the right penalty, I'm correcting the objective. And sometimes the feasible set is complex. For example, in unit commitment, we might have many disconnected components. And if I do a convex relaxation, those points would be hidden. To be able to find those points, we need valid inequalities to chop off from this feasible set to be able to recover the faces of that thing. So that's the valid inequality over there. So it was about like 10 years ago that Stephen Liu and I were interested in trying SDP for power. And SDP was going on like probably for 20 years. And we said, let's try it on benchmark example and see what happens. We were happy to see that SDP works on data for IEEE systems. And that means I have a non-convex optimal power flow problem as an example. I can use off-the-shelf solvers to get a local solution. It might be global, but I don't know. We solved SDP. We found a rank 1 solution. We decomposed it. We got a solution that is guaranteed to be global. Then we were able to prove a number of things. For example, if the price of electricity is non-negative for distribution network, this idea works. If the price of electricity is non-negative and we have enough power electronic devices for transmission network, it again works. So we had an idea that was heuristic back then. It works on some examples. We were happy about it. And we had some partial justifications for the success of this. And later on, we wrote a paper for Science Journal of Optimization, which characterized the success of this. We came up with the notion of sign-definite sets and realized that sign-definite optimization is easy. SDP works. And we have sign-definite property in power due to passivity. So there is some hidden structure in power. The infrastructure is passive. It doesn't generate energy. If I send power from point A to point B, I lose a part of that through transportation, but power doesn't come out of somewhere in the line, and that's a passivity. Because of that, we have some sign-definite property, and that explains why SDP worked in some benchmark examples. But the bad news is there are counterexamples. Some of the assumptions, like positive LMPs, are not always satisfied. So those problems are hard. And maybe we cannot find a global solution in a reasonable amount of time. What if we have a compromise and find a near global solution? So we came up with the idea of penalized SDP. We tried it on different systems like polished grad. For each of them, we were able to find a solution with global optimality guarantee of at least 99%. And then we were able to generalize it to other problems, like unit commitment, state estimation, security analysis, optimal transmission switching. So it's not a method that is another hammer just for one problem. It's a universal method that applies to a broad set of problems. And we saw that there were a lot of activities in academia and industry around this. Especially FERC was supportive of this. There were more than like 100 talks on these ideas by different people in the past 5 years. And eventually, our PIE started a 4 million cash prize competition on this 3 months ago for the best algorithm for optimal power flow. So it's not about this idea or another idea. It's just about the opportunity that what industry does has a lot of room for improvement. So how can we design better algorithms? So inspired by this success story, I want to talk about, a scientific reasoning for SDP or how to make it work for hard problems. And to be able to do that, we need two notions in graph theory. One is called tree-wets, the other one is OS. So what is tree-wets? So tree-wets, has different names in discrete optimization, in graph theory, machine learning, but they all imply the same thing. And that's the boundary between easy and hard problems. Like, how do I know a discrete optimization problem is easy or hard? So this notion was invented to partially answer this. So given a graph, like graph in the left, maybe it's not a tree, but I can go from vertices to super vertices, that we call them bags of vertices, to make a tree out of this. Of course, we have to satisfy some sophisticated properties. Then I can look at the size of each bag, calculate the maximum, -1, that would be the bets or tree. So if I start with this one, each bag could be like 2 vertices, like this. Then I should satisfy some properties. The size of each bag is 2, -1 is 1. So tree-wet is a single number associated with each graph. Another notion that is more recent, this came out of the math community in 2009, is called OS, or ordered sequencing of vertices. So given a graph, I can pick a number of vertices and order them. And I have to satisfy, again, a number of properties. It turns out that most of the time I cannot order all the vertices. I look at the maximum sequence that I can pick. For example, in this case, it's 2, and the other one is 3. That's called OS. So why do we care about these things? It turns out that those are two notions that talk about sparsity. So if you give me a graph, I can count the number of edges. I can calculate the average degree. These are really basic ways of calculating sparsity and are not helpful for answering important questions. But it turns out that very sparse graphs have low tree-wets and high OS. So these are two meaningful notions of sparsity that are connected to the area of low-rank optimization. So let's see how it's related. How is graph theory related to continuous low-rank optimization? This is a canonical problem in the signal processing and machine learning community. It's called matrix completion. It was very popular 10 years ago, inspired by the Netflix competition. The problem is as follows. I have a matrix that is partially known, like the blue entries are given. Question marks are to be designed. I have to design them in a way that the matrix is low rank and is positive semi-definite. So there are many, many methods to solve this. This is a hard problem. But it turns out that this is related to OS and tree-wets. And the way that it's related is the following. We map the location of blue entries to a graph. We do a tree decomposition, so we get bags of vertices. Some bags are bigger than the rest, so we add new vertices to make all bags have the same size. And that means I'm adding new rows and columns. I solve a matching problem over the graph. That means I'm identifying some entries there. Those are the red entries. I solve a convex optimization over the red entries. Then in the paper that was published in Science General Optimization, we were able to show that this solves the matrix completion problem. And everything is related to the size of a bag, and that was tree-wets. So indeed, there is a good connection between graph theory and low-rank optimization. And how is it related to the previous story? You give me like optimal power flow, unit commitment. I can write it in a quadratic way. Then I can do SDP. Then I know I have some natural sparsity coming out of the infrastructure. What I can do is that I go from that W to a bigger W that I call it W bar, that I add rows and columns. I identify the red entries as a penalty. By working through it, we can show that we have a solution whose rank is upper bounded by OS, which is also upper bounded by 3 bits. So this theorem by itself is really important. It says that a sparse optimization has an SDP relaxation whose rank is upper bounded by 3 bits. So let's see how important this result is. So we can calculate 3 bits for OPF, for unit commitment, for transmission switching, for any problem that you have. That captures some notion of complexity. So what is the 3 bits of real-world systems? The 3 bits of a big part of European grid, we calculated that is 35. New York grid is smaller, but it's more congested. That's about 40. So these are systems with thousands of nodes, but 3 bits is a small number. That means if I solve SDP, I may not get rank 1, but it's guaranteed to get a low rank solution. And there was another nice work, studying the problem from an orthogonal direction by Danby and Stugg at Columbia University. And he showed that when the 3 bits is small, you don't need to solve SDP. There is an LP formulation that solves it precisely. So when the 3 bits is small, there are different methods to solve it. You can use LP, we can use SDP, different methods, but 3 bits captures complexity. So far the conclusion was that because of the 3 bits of power network being small, we have a low rank solution. But in reality, I care about rank 1. How can I go from low rank to rank 1? I can add a penalty to the objective, and our penalty is linear in terms of the entries of a matrix when the entries where the coefficient should be designed. So let me pause here and explain what we're doing again. So I start with a hard problem like OPF. I make it quadratic. I do matrix optimization. I derive the rank constraint. I have to compensate for that one. And that compensation is a penalty. That penalty has a bunch of coefficients in the matrix M. I should design it carefully. That's about prior knowledge. If I design it carefully, this idea works. So let's start with an initial guess for the solution, like X star. That's a guess. It may not be the true solution. Based on that, I design the penalty M, and then we can show that there is a region around that point. If the solution is in that non-convex region, the penalty works. So based on the prior knowledge, I can tell you what I can do, what's the best thing that I can do. And recently we wrote a very detailed paper that I just summarized it in this box. It's for arbitrary polynomial optimization, but it applies to that problem as well. It's called sequential penalized SDP. The idea is the following. I start with a point that may or may not be feasible. I design a penalty. I solve penalized SDP. I get a solution, and based on that, design a new penalty. Then I solve penalized SDP. Based on a solution, I design new penalty. It's guaranteed that this idea works. So NP hard problems are hard. Some instances are hard. You cannot solve it in one shot. You have to solve it sequentially. And this is one way of solving the problem sequentially. So in Power, we tried it on different systems, like more than 7,000 scenarios. Even one-shot penalty worked all the time. But there were some counter-examples that were synthetic. One-shot penalty doesn't work. So what we did, we considered a famous library that is called QPLIB. And this library is a benchmark of quadratic programs that are really hard. And we tried to compare sequential SDP against two off-the-shelf solvers. Most of the time, these solvers just failed. They didn't give us anything. But this sequential SDP, after at most 20 rounds of iteration, gave us something that with optimality guarantee of like 96% or something. So this sequential SDP really works. So far I was talking about just optimization, that if you have a hard problem, if it's a sparse, 3 bits is one way of capturing a sparsity, we can do SDP or penalized SDP. So we've been working on this idea for a while, but then it turns out that power system is not just about optimization, it's about decision making. And one of them is data analytics, that we collect data, we want to get information out of this. And there is an underlying model that could be nonlinear, noisy, and more importantly, subject to bad data. So what is bad data in power? Some sensors might be broken, and more importantly, someone could have hacked into the system. So I, as an ISO, collect a lot of data. And especially these days, there are so many sensors, there are communications. How do I know that the data is trustworthy? A part of data could be wrong. So how can I delete that part? So I start with measurements. I have an unknown state. The equation is now linear, like assume is quadratic. We have noise. A subset of equations are subject to bad data. Like 5% of them are subject to bad data. How can we detect this? So that's the famous canonical problem in machine learning. There are many, many statistical methods, but they don't come up with deterministic guarantees. We want to come up with deterministic guarantees. Again, you can use penalized SDP, go from a decision-making problem to an optimization problem. We need to have two terms in the objective, one taking care of non-convexity, the other one taking care of rejecting bad data, and the coefficient should be designed based on the prior knowledge that we have. It turns out that if 5 hideous conditions are satisfied, this idea works. Of course, it's really hard to check all these conditions, but for Gaussian system, we can simplify and come up with a simple takeaway. If the number of bad data equations is less than a square root of the number of good measurements, we can detect it. So if you give me a long list of measurements from different sensors, if 5% is wrong, I don't know what combination, I can detect it. So that's how we can characterize it. So this is a real-world simulation in a small European network. Up to 150 equations are completely wrong. An adversary has hacked into the system, 150 equations are wrong, we can detect it, and that's a nonlinear model. The estimation error is 0. So this penalized SDP comes with deterministic guarantees. And there's another paper that we wrote on cyber attack, that once we know this, what's the worst attack that we can have on a system, and what's the best decision that we can make to just go around that one. So that was joint work with KTH, so I'm not going to talk about it, but we can do a lot on penalized SDP.
Quick question.
Yes?
What does Gaussian system mean?
So the Gaussian system, that's a very good point. Here, this MI for us in power is a sparse. If I assume that MI is Gaussian, we can simplify this. So that's Gaussian. The model from which we get the data. If the underlying model is Gaussian, then we can talk about it. So this is deterministic, that whatever MI you give me, I have to calculate some coefficients here, like rho, delta, these things. But if I assume this is Gaussian, I can calculate some numbers like expected value, variance, and say with a high probability that happens.
But noise is not Gaussian. Noise is stochastic, or
so that's another good thing that I quickly went over. So we assume noise here. So there are two kinds of noise: dense noise that appears everywhere, and a sparse noise that is engineered. So we don't make any assumption on the sparse noise or bad data. It could be a small or large. But for dense noise, we should either assume it's 0 or it's Gaussian. So that's another thing. The small noise is Gaussian because that's on top of what we get from a probe. But the bad data is something that we cannot make any assumption is probability distribution. Yeah, that's a very good point here. And then, so this is more like classic state estimation, that how to get reliable information from limited data. In the future, we are talking about abundant data, a large volume of data. So now the question is completely different. When we have PMUs everywhere, we are not talking about this much data or that much data. We are mostly worried about, okay, can I trust data? So how can I solve a problem like this? So it turns out that we can come up with a new method, and that method is the following. If I have a lot of data, non-convexity goes away. So I define W as VV transpose. So V is the vector of voltages. W was the inner product. I get a matrix. Some elements of this matrix corresponds to physical things, like voltage magnitude, like line. I call that X. So X is a collection of variables that are important for us. Then I can solve a two-stage problem. From data, I can estimate X. That's a lasso problem. From X, I can estimate W. That's a matrix completion problem. So I can solve two separate problems. So a lasso problem that finds X based on least square, and another one norm term taking care of rejecting bad data, and then solve a matrix completion. If you have a lot of data, this works. So first we tried it on a real world system. This is an RTE system with about 3,000 nodes. Up to 1,000 equations were completely wrong. So that's a large number. Still, up to 1,000 equations were wrong. Still, the estimation error was really, really small. So this idea looks really plausible, that I don't solve a state estimation in one shot. I come up with a linear transformation in X, find the best guess for the X, then find the best guess for W, and then do a decomposition. Then we said, okay, can we prove something about this idea? We came up with the notion of attack, that bad data, if it's random, is easy to detect. So if you give me a bunch of random equations and say this is deleted, that's like this, I can easily figure things out. But when an attacker has engineered the attack, it's really hard to detect it. So we said, what if a part of the network is attacked in the worst possible way? We can define the boundary of attack. We can talk about inner boundary, outer boundary, and come up with a new notion of mutual incoherence. This is different from what people do in machine learning. It's just engineered for this problem. And if the mutual incoherence on the boundary is less than 1, we can detect it. So if you give me a power network and a part of the data is attacked locally, an attacker would assume that that miscommunication or miscalculation propagates. But this idea guarantees that that's not going to happen. If we solve that lasso problem, we can find the boundary of attack and remove that part from the system. So using this notion of mutual incoherence for a graph that we came up with. So far we talked about two problems, optimization and data analytics, and SDP was everywhere. But one important question is SDP practically useful? So, many people in industry would say LP is the best thing to go, QP is okay, anything beyond that is too complex. They're not willing to solve. So what's the complexity of SDP? So let me just skip, okay. So what's the complexity of SDP? So SDP, or semi-definite programming, includes linear programming, quadratic programming, quadratic to constraint quadratic programming, the second order comp programming. So it's much bigger than the previous classes. Can we really solve this efficiently? If we can solve it, then we are able to solve all previous classes efficiently. Maybe that's too ambitious. So one thing that people do all the time is, okay, if instead of working on a big matrix, I can work on sub-matrices. I don't need to solve a big problem, because if I find sub-matrices, I do a matrix completion. And then the idea of distributed computation can come out of this in this context. There are nice papers by Stephen Boyd, by Levin Vanderby, by different people, Goldfarb at Columbia, on how to do distributed computation for matrices. Especially, they were inspired by big data problems. And what we came up with was that a first order method based on ADMM, where we can show that all we need to do is eigenvalue decomposition. So if you do the first order method right, and we have a solver that can do eigenvalue decomposition, we can solve big problems. So we wrote the code in C++. We did testing on Amazon server with 36 cores. We consider a problem with about 50 billion variables. This is the size of US if you do a square matrix. You can leverage a sparsity to go from billions to millions. If you count the number of flops for Mosaic, SDP, Tree, Sojoudi, it takes months. So these are a hard problem. But first order method on Amazon solve it from 2 minutes to 20 minutes, depending on how well conditioned the problem is. So these first order methods that people use for data analytics are really, really powerful, but there is a caveat, and that's the following. First order methods have low complexity per iteration, but they need so many iterations. The complexity per accuracy is exponential. They say 1 over epsilon. Then people will say we use second order methods. When we don't need many iterations, the complexity is log of 1 over epsilon, but complexity per iteration is suddenly n to the 6. So that's a trade-off. That's why Mosaic, Sojoudi, SDP3 cannot solve it. So we said, what's the true complexity? We don't want to take so many iterations. At the same time, we don't want to have complex iterations. So can we somehow combine it? We said, let's do a case study. We consider different power systems. with different sizes. We said we put the size on the horizontal axis and solve it using mosaic and put the time on the vertical axis and just draw it. Suddenly the line became linear. We said the complexity was supposed to be n to the 6, but suddenly the empirical complexity is linear. This is very strange. Then we wrote a long paper that is more, yes?
It's a log graph.
This is, yes, this is log, but yeah, if you look at the slope, it's 1. Yeah. This is linear. This is linear. This is something, yeah. This is multiple graphs. The graph I'm talking about is this graph that is linear. Yeah, we have to go over this, but the graph for this one, that is just one of the lines, if you consider it linear, forget about the log, that becomes linear. And I'm going to talk about it later on. So I'm going to give you the exact number for this graph. Yeah, maybe this is not the best representation. Yeah, yeah. Okay, let's explain it here. There is a circle that is called Dirac, and the cross is reformulation. So if you pass the problem directly to mosaic, it's not linear. You have to do it. You have to calculate the dual and do a clique conversion. If you do it, suddenly it becomes linear. So the next slide, makes it more clear. So what we showed was the following: that the complexity is not n to the 6. It's the product of 3 terms. So we use about like 10 lemmas to get to this. So for us, this is really fundamental, because if we solve SDP, then we know how to solve LP, QP, and other things. So it's a product of 3 terms. One is about block intersection graph. The other one is tree vest. There are many, many things. In the context of power, for example, the previous graph, we know that power systems have bounded tree vests, have bounded degrees, have bounded number of constraints per node. That means every term over there would be bounded. And because of that, the time complexity of solving SDP, so the memory complexity is linear, the time complexity is at most n to the 1.5, log of 1 over epsilon. So this complexity is better than even solving a generic LP, because generic LP is n cubed. And that's exactly what we can observe here, that's between n and n to the 1.5. Then in a related work, related in terms of methodology but not application, that was joint work with Prof at Berkeley. We spent years on transportation. We said, let's try this on optimizing, the congestion at different intersections. So we considered the data for Berkeley, Manhattan, Los Angeles. We said, this is again non-convex optimization, but we can convert it to, polynomial optimization. We can use SDP. What's the actual complexity? Again, that was linear for systems with about like 11,000 intersections. It's somewhere 12,000 intersections. So these are big problems. SDPs with 11,000 rows, 11,000 columns, and we can solve it in a reasonable amount of time. And the last thing that I want to mention here is that, okay, so far I was trying to advocate for conic optimization or SDP, but if we go to the machine learning community, most of them don't even believe convex optimization. They would say this is too complex. Just use gradient method, a stochastic gradient method, the simplest algorithm possible. And most of the time it works. They do training of deep neural net using the most basic algorithm, it works. There are a lot of fine-tuning the parameters. There's an art there, but we want to understand when it works and what to do when it fails. So local search algorithm for global optimization. So their canonical example is a problem that is called matrix recovery. Like a state estimation is a special case of this. I want to recover a matrix from linear observation of entries, and the matrix is low rank. They do 2-norm approximations, a formulation based on rank. They do nonlinear least square. They do nonlinear absolute value. So these are all hard problems because they're highly non-convex. If you draw the function, it looks like this. It's very complex. They're far away from being convex, but they use local symmetry, which works. And the question is, why does it work? So, and they already know that 1 norm is much better than 2 norm. 2 norm fails very quickly. 1 norm is much better because it's robust. But if you look at all the recent papers in NIPS and ICML and machine learning communities on the middle problem, is 2 norm, because for 2 norm, they know how to calculate derivative, Hessian, all these things. For 1 norm, they cannot. So the question is there any way to deal with like 1 norm or non-smooth optimization? So if we go from 2 norm to 1 norm, the surface gets much more complicated. And then we cannot talk about derivative or second derivative in an easy way. So what we came up with is the name that we gave it is called global function. So we have the class of convex optimization, then Gaussian convex, and then quasi-convex, then S3 convex, a star convex, all kinds of classes. It turns out that this class, a class of problem with no spurious solution, is much bigger than any other class. And then, so that was one of our NIPS paper this year, then we were able to prove things about like point-one convergence, uniform convergence, change of variables through homeomorphism, and all kinds of things. And based on this, we realized that, so this class is much more complex than convex optimization because it could be nowhere differentiable, for example. It could be much more complicated than convex optimization. Like this could be neural net. It's much more complicated than convex optimization. How can I come up with guarantees for functions like this? Then it turns out that like matrix decomposition, tensor decomposition are all global functions. And there was a follow-up paper at UIUC just a month ago which says that even deep neural net are global functions. So we came up with this name to study tensors, and it turns out that even like deep neural net have the same property. And so that's one direction that we're working on to really understand when we can do local search algorithms. Forget about SDP. Another thing that is important is there is a boundary between easy and hard problems. And Emmanuel Candace came up with the notion of restricted isometry property to somehow characterize this. So, when we talk about conference sensing, matrix recovery, there is a parameter that talks about the complexity of a mapping. And in recent years, there are so many papers on this. Like NIPS 2016 Best Paper Award was a conservative bound on this. So it's very important for us to somehow come up with an understanding of this boundary. If you give me a problem, like a state estimation, is it easy or hard? So I have to calculate that number. What number is good? So we were able to show that, there is a sharp bound that is necessary and sufficient. So that's another NIPS paper that we had this year. We somehow find it not the conservative, but the right sharp bound that is telling us this class of problems are easy, this class is hard. Most of the time, in NP-hard problem, finding the boundary by itself is NP-hard. But here we are lucky that we are able to characterize it. And in terms of power, because this is a power workshop, this picture illustrated well. If you go down, it's the amount of data that increases. White color means success rate, and this is local search algorithm based on prior knowledge. If the amount of data is higher than 2.5, the ratio, local search algorithm works all the time. ISOs have been using local search for state estimation for 50 years. They never complain about it. And you will say, why does local search work on a highly non-convex problem? Because they have a lot of data. The amount of data is above that threshold, and we can explain it here. That it works all the time. We can calculate all those restricted isometry properties and say when local search works. So local search works 100% if the amount of data is higher than a threshold. That threshold is different for different networks because that mapping, we should calculate RIP. But now there is a new mathematics that explains what industry has been doing for years is scientifically justified. But then it would say, okay, what if there is an error in the model, topology error? Then that idea fails. So it's not the case that it's a perfect thing they're doing, but it works. Another thing that I just want to mention is very quickly is that, okay, talk about SDP for static problems. But when we talk about power, it's dynamics. And there is a lot of learnings in this. And learning, for example, could be reinforcement learning, neural net. When you do frequency control, you don't know the model, you have nonlinearity. And online learning is also very important. This is a neural net that we try to learn the model online. And it turns out that SDP also appears in this context to guarantee stability during learning. So SDP is not just about getting a better solution. It's also about having some guarantees on the performance of a dynamic system. So that, comes out of, IQC, integral quadratic constraint, and other things. But I just wanted to quickly mention that SDP is very powerful for optimization, for data analytics, and also for learning of a dynamic model. And the good news is there are algorithms that can solve SDP in near linear time because of the hidden structure. So it's not the worst case scenario. Real world systems are not always the worst case scenario. At the same time, if we don't like SDP, if we don't like convex optimization, local search would work if we have enough data. So then we have to quantify what does it mean? What's the right threshold? How much data do I need so that the simplest algorithm, a stochastic gradient, would work? And then there's a new, mathematics explaining when that works. And this was joint work with several people in my group and 6 of my colleagues at Berkeley, UT Austin, and KTH. And that was supported by generous grants. So with that, I conclude my talk. Thanks for your attention. I'll be happy to take your questions.
Thank you very much. Are there some questions, clarifying questions, or questions opening up to some topic of your choice? No questions?
Kind of one, if you want. So on the outliers, on detection of bad data, I understand that you need to know the dimension, the number of outliers, the small r in the formulation.
Yeah, go to, sorry. This one or another one?
No, the bad data detection, yes.
Okay. This one?
Yes. The small r must be known.
Okay, so there are two things here. So one is the one that I wrote here. The other one is, where is this? I put it somewhere, but it's not. Yeah, maybe I can just explain. So we have two methods. The first method is this one, by assuming that M is perfect. You know the model correctly. You get this result.
The dimension, I'm speaking of the dimension, the number of bad data.
Okay, the number, not the model.
Yes, the number, the dimensions.
Okay, because I thought you were talking about, so we have some capital M, so capital M is the model.
Yes.
So there are two works that we have. In the first work, assume that M is given. In the second work, we assume that we might have topological errors. So we have a similar bound, but it's not as good as this one. So, but that's one direction. The other direction is, okay, if you give me a bunch of equations, how many of them could be wrong, and still this method works? So that's the question we want to answer. So we have bad data, for example, of 5% of equation, and it could be bad, arbitrary wrong. Small numbers or big numbers, they're engineered. So is it going to work? So what we have shown is that if all these conditions are satisfied, then it's going to work. So that gives us the threshold. Is it 5%, 10%, 15%? And like for this grid, with 1,300 nodes, we have 5,000 measurements. With 5,000 measurements, we are robust to up to 150 bad data equations. So we have to calculate it for each individual system. Make sense?
Yes, but I'm not sure of that. Because it's possible to have an infeasible problem if you have a maximum transmission power, for example. If I can locate an outlier somewhere,
okay,
it's not possible to solve the system because there is no solution.
Oh, no. So maybe the problem is different. The problem that I'm talking is that there is a system going on. There's an underlying solution that I'm trying to find based on the data. So the solution must exist. So I assume that there is a V that is the current state of a system. So I'm not trying to do a forecast about something that might be infeasible in the future. So there is a system with a current V that exists, and based on the current measurement, I want to have the best guess at that one.
But due to the bad data, the system...
So bad data just says measurements are wrong. But doesn't mean the solution doesn't exist. The solution is just the operating point that is just running now. Yeah, maybe it's a different context, yeah.
Warren?
So I'm not a power flow expert, but I do have a big simulator that solves power flow problems. Now, isn't it the case that in power flow we can model it as this big optimization problem, but in fact, there's actually a real physical system where the grid is somehow finding a solution which we're characterizing as an optimization problem, but there's no guarantee the grid finds that optimal solution, right?
Okay.
Yes.
It evolves.
That's why we want to find an algorithm that guarantees that. So what you're saying, for example, is that M. That M is, if I'm the operator, I have some imagination about the actual model, but the actual model is the physics that I don't know. For example, I don't know the actual temperature on the street. So there is some error in that M. Because of that, simulator might find something that doesn't correspond to the actual thing.
Well, let me take you a step further. Let's say that I'm really simulating this in a second-by-second time step. Isn't it the case that the solution at 1 second depends on what the solution was at the previous second? I mean, it is a physical system. It doesn't jump from here to here. It evolves because it's a physical system.
If your algorithm uses the prior knowledge, like if the algorithm is a local search, as we say, the solution now doesn't change too much in 5 minutes, then that's true.
No. Let's not talk about the algorithm.
Okay?
Let's talk about the physical system.
No, if there is a fault, there could be a jump. The voltage collapse would say you can go from 1.1 to 0.6.
Yeah, I understand. But let's just talk about under normal operating conditions.
Yes.
It's evolving, the loads are changing and whatnot, and the system is going to move from one solution to another. I mean, the real world has lots of examples in molecules and whatnot where they find local optima.
Yes, that's true.
And they evolve from one local optimum to another as exogenous forces push them, but they don't find global optima. They find local optima.
Yes.
I've never seen this community even acknowledge that behind all this is an actual physical system that where the solution at a time t really does depend on what the solution was at some time increment before that. Isn't this really physically what's happening?
Yes. So if you look at this RPi Grand Challenge that Tim Hadel started and then Corey Hitman took it over. So what Tim Hadel had in mind was a one-shot OPF competition. Then Corey broke it down to a multi-year competition where first year is a static problem, second year and third year would be more realistic, and then you talk about all these temporal constraints and what happens over time. So in reality, what operator, like what PJM does is doesn't solve this one-shot problem. It does it for 3 time steps because there is a correlation over time.
But are people in this community getting to the point where depending on the solution here, it'll affect the solution here? Because underlying it, it doesn't magically jump from one to the next.
Yes.
Barring massive exogenous inputs, it's evolving.
Yes, that's true.
And so, in other words, the goal of a global solution, is that really the right question, or should we be asking the question of
what
dynamically evolve?
So what you're saying is, if at 5 a.m. I find the wrong solution, I should iterate over that for 12 hours and continue tracing that wrong local solution. And what we are trying to advocate is that, okay, every 5 minutes, I can use the previous solution as prior knowledge, but that might be wrong, because maybe 5 minutes ago I didn't find the best solution. So we can trace back a solution and say this is a trajectory. 5 a.m. I didn't find the best solution. Let's iterate over that. That's physical. So there is another thing that I have to make the point here. There is a difference between planning and the actual thing happening. So power flow is planning, so they don't implement it. So I'm not worried about it. This is about the actual number that they get at the current time. It's very important to find a global solution because local is meaningless. That's about like what's the current inside this one. Local solution doesn't mean anything.
I'm sorry, I feel like I'm going to completely disagree. That if the system is an actual point at some time t, if you go from t to delta t, physical laws will drive that evolution.
Yeah, that's true.
In other words, the notion
but those are lower and upper bounds on power. So operator would say every 5 minutes, I optimize power based on P, have a lower and upper bound. Lower and upper bound takes care of 5 minutes ago. So they know that they cannot have a ramp constraint. They cannot have a jump.
Let me not do 5 minutes. Let me do 1/10 of a second. Okay, so I'm evolving in micro time. Hertz level. Okay, the way the power system really works.
Okay.
The thing is, it's going to be at some solution, which is generally not going to be some global optimum. It'll be some solution.
Okay.
And as the forces change, it'll evolve to another solution, which is probably, again, not a global optimum.
Okay.
I'm trying to...
But do we care about that solution? Do we want to implement that solution every 5 seconds?
It's not up to you to implement. It's up to physics to figure out what they actually want to do. Okay, this is not something for us.
Okay.
We don't get to choose how the power grid actually
Yes.
decides.
Okay.
Somewhere
So now I
you
know
have
what
to
you're
model the
talking about. So the way that operators work is that they have a combination of optimization and control that takes care of stability. So there is an actual dynamic controller that takes care of frequency, voltage, etc. Every 5 minutes, they try to optimize their reference, and meanwhile, you would say everything else is transient. I don't care about it. I know that in 5 minutes I want to reach there. If you make it every 10 seconds, you're just mixing up stability with optimization, then you cannot track it. Then I agree with you, global solution is useless.
I'll take
Because we cannot take care of it.
Yeah, we can
take it
actually
offline.
discuss that. We're here for a whole week, so we can touch some other topics. I think it's Simon and then Florian. Yeah, Simon.
So a comment followed by a question. So the comment being that I guess there is a discrepancy between whether you're considering optimization over money, in which case this holds, or kind of some control algorithm, or state estimation. If you're doing state estimation, I would guess that you would try to find the global optimum at every instance, because that's the best knowledge you currently have, and you might have been wrong all the time in the past. The question here would be, if you say that you can detect a certain number of bad measurements, right?
Yes.
I guess you could always find a few very specific targeted bad measurements that could be stealthy in the sense that they would,
Yes, that's true.
be invisible, right? So
what operators do is hypothesis testing. So they get the data. They would say, okay, I define a threshold. I do a statistical testing. I would say these 5 measurements are completely off. Just delete it. Then they solve a nonlinear least score on the remaining data. But this doesn't come up with any deterministic guarantee. It comes up with probabilistic guarantee. That would say 99% of the time it works. But this is not how physics works. We want to make sure it works all the time. There are good recourse actions. So what we want to say here is that there is a threshold, like 5%. No matter what 5% combination is wrong, it's going to work. Even if an attacker carefully designed that 5%, first of all the equations, and second the values. So but it's true that they're doing it, and there are some equations that are easy to detect. But if you look at the literature of attack, is here, the literature of cyber attack, it turns out that if you pick like 5 equations at the substation and carefully manipulate the numbers, you can deceive the operator. So those are things that we want to avoid. And that's why we want to find the boundary of attack and come up with deterministic guarantees.
but is there a way in which you can ever, I mean, you can always, I guess, in a localized subsystem, create an attack if you have full knowledge, right?
That's true.
That is physically correct, or at least seems physically correct, right?
Yes.
Okay, how can you ever detect those?
Okay, so that's a very good point. So if you look at the notion of mutual incoherence in machine learning, you would say if mutual incoherence is satisfied, you can detect all the wrong equation precisely. But in power, that's not possible because of unobservability. If I have a region, there are things going on inside that they legitimately satisfy laws of physics. You cannot say if that's correct or not. So what we want to detect is not all the measurements, it's just the boundary of that. I want to draw a circle and say I cannot say much about inside this circle because of unobservability, exactly the point that you mentioned. But I know that that circle is a problem, and the rest is healthy.
I guess we'll need to take this offline, but yeah, thanks.
Does Florian have a question also, and then?
Yes. At the very end, he offered this nice snippet on reinforcement learning and said that SDP is also important to guarantee some robust stability during reinforcement learning. Can you offer some little bit of details?
Yes, actually that's one of the things that we work a lot, but that could be has a lot of details, but I can tell you, okay, here, what it means. So in reinforcement learning, for example, the operator would say, I want to do frequency control, I use like DC model, I modulate, I have the controller, I apply it, because of the physics, it doesn't operate the way that they want it. So we have to come up with a semi-model-free approach that I have some knowledge, I can do linearization, there is a nonlinearity I cannot take care of. So there is a policy that I want to learn to achieve some, some goal, and there is some environment that I have some knowledge about it. So we can do, for example, the way that we did it is that, okay, we can talk about the gradient and parameterize the policy, do optimization over that. The challenge is something that is very well known in that community, which says that you cannot guarantee safety. As I take actions and apply it, then a little bit of disturbance would kill the system. So I can be very ambitious in exploration, or I can be, very conservative, and that makes a big difference. I'm trying to learn very well, suddenly I have instability. So now the question is, so there is something in that literature that if you have different layers, you can talk about derivatives and say, if this layer has a big change, it affects the other ones. I can have to put some values on derivative and propagation, the Lipschitz constant, and those things to make sure we have a safe learning. And that is related to integral quadratic constraint. That's the control theory for a completely different reason, and that can be formulated at STP. So you want to use a neural net to use a model, to learn a model for frequency control, but STP is inside this and helps you to learn it like this with a guarantee.
And is the SDP then some sort of a posteriori stability check under these and these parameters?
So this SDP helps you to find some parameters that, so in this learning, at every iteration, you have to revise your action. That's an optimization problem. So you can solve one SDP before offline, or just incorporate SDP at every iteration. But that SDP will tell you how ambitious should I be, so that in the future I won't face instability.
Thank you.
You have a question or something?
Maybe a very quick one. So you say you can detect, right? So what does that really mean if you have noise? You can never be for sure, right?
Yes.
So what does it mean by you can detect?
Okay, that's a very good point, actually. Okay, so I don't have the equation here, but I can tell you what happens. So so we solve this SDP, or it's not exactly SDP, but some conic optimization. It turns out that if we don't have dense noise, just bad data, if these conditions are satisfied, we can detect it precisely. And then if we have dense noise, so what we do is actually a two-stage. So we solve a problem, and then we say a bunch of equations are wrong, just delete it. Solve another problem. As you said, when we have noise, we cannot detect it precisely. Then we would say the solution that we get compared to that solution is upper bounded by density of the dense noise. So if you have dense noise, we can never ever detect anything precisely. So there is a difference between detecting bad equations and finding the exact solution. So I can detect what equations are bad depending on the magnitude here, but I cannot find the exact value. There is an error there.
There's always relative probability, right? I mean, there's no way you can say, I can for sure to detect. You may be wrong. You may be, the attack is not there, you declare.
Yeah, so yeah, that's a good thing. So this is a deterministic theorem that just assumes that we have bad data.
Right. That's
This is a stochastic one, that there are some coefficients, and that's with the high probability this happens. And that high probability and coefficients is really about this. So the values for that makes a difference. If this dominates this one, of course, we cannot do anything.
So the understanding should be when the noise variance goes to 0, that's correct?
Yes. And if the noise is modest, that's going to shift the solution a little bit.
All right, but I think we need to close the session. Thank you very much for a good talk and for a good discussion.